Okay, so problem 1. I find it's always a good idea to start with a diagram. So in this case, we've got two express telegrams heading towards the Earth. Okay, so here's the Earth, and we've got one telegram coming from Mum. So let's let it have speed Vm, and that's equal to 0.8 c, and it's traveling towards the Earth. And then we've got another telegram coming from Dad. So let's let it have speed Vd, and that is equal to 0.5 c, and it is also traveling towards the Earth from the same direction. And what we want to know is what would be the velocity of Dad's telegram as measured from Mum's. So we actually want to transfer ourselves from the Earth's frame of reference to Mum's frame of reference and then measure Dad's speed. So we're going to need to use the equation that Vx prime is equal to Vx minus u over 1 minus u Vx on c squared. But let's go through and define what each of these is going to be in our system. So Vx prime, that is the speed of Dad's telegram as measured by Mum's telegram, which is what we're trying to find. So the speed of Dad's telegram as measured by Mum's, which is what we want. Okay, now Vx, that is the speed of the object in the original reference frame. So that's the speed of Dad's telegram in the Earth's reference frame. So that's equal to Vd, which is equal to 0.5 c. And u, that's the relative speed of the reference frame. So in this case, we're going from the Earth's reference frame, which we took to be 0, to Mum's telegram's reference frame, which is 0.8 c. So that's u. So now we've worked out what everything in here is. So now we just need to put it in. Okay, so Vx, that was 0.5 c, minus u, which is 0.8 c, over 1 minus 0.5 times 0.8 c squared, because they're both c, so c times c squared, over c squared. These c squareds cancel out, and so we end up with minus 0.3c over 1 minus 0.5 times 0.8, so that's 0.4. And so we've got minus 0.3c over 0.6, and so that's equal to minus 0.5c. Okay, so that's how we solve 1. Okay, so problem 2. Now, I always like to start by drawing a diagram. So here's Earth, and towards the Earth we have two messages approaching. We've got Dad's telegraph approaching with speed Vd over here, and Mum's telegraph approaching from the opposite direction with speed Vm. Now, in this question, we're told that the relative speed is equal to 0.7 c. And what that means is that the speed Mum measures for Dad is 0.7 c. So looking at our equation, Vx prime is equal to Vx minus u over 1 minus uvx on c squared. Vx prime is equal to 0.7 c if we're considering Dad's speed as measured from Mum's frame. Okay, so in this question we're going to move from the Earth's frame, the unprimed frame is the Earth, to Mum's frame. So the primed frame is mum's frame. Okay, so going back to the unprimed frame to define what Vx and u is. Okay, so Vx, that's the speed. In this case, we were measuring Dad's telegraph from Mum. So in this case, Vx is still the speed of Dad's telegraph, but it's from the Earth. So let's call that Vd equals the speed of Dad's telegraph as measured from Earth. And u, that's the speed of our new reference frame relative to the Earth. So that's the speed of Vm. So that is equal to Vm relative to the Earth. Now, in the question, we're told that they come from opposite directions, but that they have the same speed as measured from Earth. So that tells us that Vm is equal to minus Vd. The minus because they're in opposite directions, but the absolute value, the speed, is the same. Okay, so now we've defined what everything is. This is what we're trying to find, Vd. We want Vd. So we can substitute this in and try and solve it. Okay, so we've got 0.7 c is equal to Vx, which is Vd, minus u, which is minus Vd in this case, over 1 minus u, which is minus Vd. So that gives us a plus down the bottom, Vd squared on c squared. Okay, so we've got 0.7c is equal to minus, that's plus, so this is 2Vd over 1 plus Vd squared on c squared. Okay, now let's rearrange this a little bit. We can write this as 1 plus Vd squared on c squared equals 2Vd over 0.7c. And now let's let x equal Vd on c. So what we end up with is 1 plus x squared is equal to 2 over 0.7 x. So we can write x squared minus 2 over 0.7 x plus 1 is equal to 0. Okay, so this is now in the format of something that we can solve with the quadratic equation. So the quadratic equation tells us that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And in this case, looking at this, a is the thing in front of the x squared. So a is equal to 1. B is the thing in front of the x, so that's equal to minus 2 over 0.7. And c is the thing in front of here, so c is equal to 1 as well. So we have x is equal to 2 over 0.7 plus or minus the square root of 2 over 0.7 squared minus 4 over 2. So this is equal to 1.428 plus or minus, so 1.428, that's just 2 over 0.7 divided by 2, plus or minus, then we solve this on the calculator, 1.020. And now if we were to add these, we'd end up with a number bigger than 1, which would be bad because it's x is equal to the velocity divided by the speed of light, so we'd end up with the speed of light. So we're going to have to subtract them. So we end up with 0.41. So that tells us that Vd, the speed of Dad, is equal to, well, xc, and we've just found x here. So it's 0.41c. So that's the speed here, and we know that the speed of Mum is in the opposite direction, but it has the same magnitude, so that's 0.41c. So their speeds are plus and minus 0.41c. Okay, we're on to question 3. In this one, we're told that the Sun orbits the centre of the Milky Way with a speed v of 250 kilometers per second. So we've got the center of the Milky Way here, and we've got the sun orbiting it like that. And we're asked to find the percentage difference between the relativistic and Newtonian values of momentum. So what we want is the difference between the momentums over the momentums. So we basically want the relativistic momentum minus the non-relativistic momentum, the difference of these two over p. These will be very similar, so it doesn't matter. We can use either this one or this one for this p. Okay, so what we should start by doing is write down expressions for the non-relativistic and for the relativistic momentum. Okay, so for the non-relativistic Newtonian case, we know that momentum is equal to the mass times the velocity. In the question, we're given the mass. The mass of the sun is equal to 2 times 10 to the 30 kilograms. Okay, so we can come up with a value for this if we want to. We don't have to at this stage, but we can. So 2, sorry, that's not a 3, it's a 2. 2 times 10 to the 30 times 250, and then this is kilometers per second, so we times it by 1,000 to get it into meters per second, and this gives us the momentum, which is equal to 5 times 10 to the 35 kilogram meters per second. Okay, and then we need the relativistic momentum, and that's equal to mv over the square root of 1 minus v squared on c squared. So that's equal to mv is the same thing. So it's still 5 times 10 to the 35. But now we're dividing by 1 minus v squared, which is 250 times 1,000 over c, 3 times 10 to the 8, all squared. And so this is equal to 5 times 10 to the 35 over, putting this in the calculator, we end up with 0.9999999652. Okay, so now we've got expressions for these. So now we're just going to put everything back in here. So we end up with 5 times 10 to the 35 minus 5 times 10 to the 35 over 0.99999652 over mv. We can just use this one. These two numbers are really similar. If you type them into calculator, you end up with almost the same thing. So that can go down the bottom, and then you can see these cancel. So we end up with 1 minus 1 over 0.999999652 over 1. Okay, so now we evaluate this thing. So this thing here is the delta p over p. And when we evaluate it, we end up with 3.47 times 10 to the minus 7. And so that's the fractional difference. Now, in the question, we're asked for the percentage difference. To get something from a fraction to a percentage, we times by 100. So percentage difference is just equal to 3.47 times 10 to the minus 7 times 100. And so that is equal to 3.47 times 10 to the minus 5. Okay, so this is problem 4. In this case, we've got David, who's traveling, let's call it the x direction, at 0.75 c, as measured by some observer here. And there's Emily, so this is David. And here's Emily. And she's moving perpendicularly to David at a speed minus 0.90 c. So the negative's there because it's going downwards in the negative y direction. And the question is, how fast does Emily recede as seen by David? So what we want is Emily's speed according to David And what we have is Emily and David's speed according to some, what we're calling stationary observer here. Okay, so this is going to be a relative velocity question. It's going to be a little bit challenging just because there's two directions involved. So we'll need to consider the x and the y components separately. So let's start by considering the x component of Emily's motion. So let's the x component. Now we know for x, vx prime is equal to vx minus u over 1 minus u vx on c. So what we need to do now is work out, well, what do each of these things mean in this situation? So what we're trying to do is go from this frame to David's frame and measure Emily's speed. So Emily's the object that's moving that we're measuring, and David is the new frame. Okay, so Vx prime, that is going to be the speed of the object as measured in the new frame. So the speed of Emily as measured by David, which is good because that's what we want to find, so it's good that that's one of the things. Okay, Vx, that is the speed of the object in the unprimed frame. So that is going to be equal to, well, it's minus 0.90 cy. There is no x component, so that's 0. And u, that's the speed of the frame, the primed frame that we're moving to, i.e. David's frame, relative to this frame here. So u is equal to 0.75 c in this case. It's just David's speed. Okay, so now what we can do is we can substitute everything in here to end up with what we want. So we've got 0 minus 0.75 c over 1 minus, now this is 0 times 0.750. So we end up with minus 0.75 c. Now let's just do a sanity check. If we were David, it would look to us like Emily was moving backwards in the negative x direction. So it's a fairly big number, which is what we'd expect because we are traveling fairly fast, but it's also negative. So it seems reasonable. Okay, so now we've worked out Emily's speed in the x direction, but Emily is also moving relative to David in the y direction, so we also need to calculate that. So let's consider, let's put an apostrophe, consider the y component. Okay, so we'll need to use vy prime is equal to vy root 1 minus u squared on c squared over 1 minus u vx on c. Okay, so again, we're moving from this stationary frame to David's frame. So vy, that is, well, let's start with vy prime. That's the speed of Emily as measured by David, speed of Emily according to David. Vy. Now that's the speed of the object in the unprimed frame, and in this case it's minus 0.90 c. U is still the same. It's the relative movement of the frame. So we're going from this stationary frame to David, so it's still 0.75 c. And we also need Vx, which once again hasn't changed. That's the x component of Emily's motion in David's frame, so that's 0 still. Okay, so now we can substitute everything in, and this is what we want, so this is good. So when we substitute in, we've got minus 0.90 c times the square root of 1 minus 0.75 c on c squared over 1 minus, now Vx is 0, so this is still over 0. So we've got, this is equal to minus 0.90c times the square root of this c cancels this c, and we have 1 minus 0.75 squared. And solving this, we end up with minus 0.595c. Okay, so sanity check again. If we're David, it does look like Emily's moving downward, so it should be negative. It seems fairly reasonable. Okay, what we were asked to find was Emily's speed. So we've got the x component of her velocity, the y component of her velocity. To work out the total speed, Emily's speed, we're going to have to add these together because we've got the x1, which is going like that, vx. We've got vy, well, vy going like that, and this is what we want to find. So to find this side of this triangle, we use Pythagoras. So it's the square root of minus 0.75 squared plus minus 0.595. Oh, then there's a c in there, c squared. So that is equal to 0.96c. Okay, so final sanity check is we'd be a bit worried if this was faster than the speed of light, because it shouldn't look like things are going faster than the speed of light. It's not bigger than the speed of light, so that's good. We would expect it to be a very large number, and it is. So this seems like a reasonable answer, and it is correct. Okay, so problem 5. In this one, we have a high energy collision somewhere up high. It's 120 kilometers above the surface of the Earth. And a pion's created, and we're told that the energy of the pion is equal to 1.35 times 10 to the 5 mega electron volts. And in the pion's rest frame, the pion decays in 35 nanoseconds. So in the rest frame, the lifetime is 35.0 times 10 to the minus 9 seconds. And we're asked at what altitude above sea level, as measured from the Earth's reference frame, does the decay occur? And we're told that the rest mass is equal to 139.6 mega electron volts. Okay, so let's look at the equations that we'll need to use. We'll need to use our equation for the total energy. The total energy is equal to mc squared over the square root of 1 minus v squared on c squared, where v squared is how fast the particle is moving. And we're told that that is equal to 1.35 times 10 to the 5 mega electron volts. So let's get this into SI units. So mega, that's times 10 to the 6. So that's now in electron volts, but we're going to put it into joules. So we'll times it by 1.602 times 10 to the minus 19. And that's joules, because this is just the charge on an electron. That's how we convert from electron volts to joules. Okay, and in this equation, m is the rest mass. We're given the rest mass in mega electron volts. So we know mc squared is equal to 139.6 times 10 to the 6, again to account for this mega, and then times 1.602 times 10 to the minus 19, and that will be in joules. So now we've got both these ones in the same units. So what we can do now is rearrange this so that we end up with the square root of 1 minus v squared on c squared is equal to mc squared on e, and we've got numbers for this. So this is 139.6 times 10 to the 6 times 1.602 times 10 to the minus 19 over 1.35 times 10 to the 5 times 10 to the 6 times 1.602 times 10 to the minus 19. So if you want to save some time, you could have left them both in mega electron volts and it would have cancelled out, but I didn't in this case. You can. Okay, so solving that, we end up with 139.6 divided by 1.35 times 10 to the 5, and that is equal to 1.034 times 10 to the minus 3. And that's our value for the square root of 1 minus v squared on c squared. Now, what we know is the lifetime of the muon in its own frame. But the muon's going fast, so it undergoes time dilation. So we're going to have to look at our time dilation equation, which tells us that the time it lives in the Earth's reference frame is equal to the time it lives in its own reference frame divided by 1 minus v squared on c squared, which we have just calculated. So we've got the time in its frame is 35.0 times 10 to the minus 9 over this thing which we've calculated, which is 1.034 times 10 to the minus 3. So in the Earth's reference frame, we know that it lives for 3.38 times 10 to the minus 5 seconds. Okay, so now what we want to know is, well, how far does it travel? We know how long it travels for, and from mechanics, we know that the distance is just equal to the velocity times the time. So we've got the square root of 1 minus v squared on c squared is equal to this thing, and we can solve this for v squared. So 1 minus v squared on c squared is equal to 1.034 times 10 to the minus 3 squared, and we can rearrange this a little bit. V squared is equal to c squared times 1 minus 1.034 times 10 to the minus 3 squared, and we know c is 3 times 10 to the 8, so v is equal to c times the square root of 1 minus 1.034 times 10 to the minus 3 squared. So this gives us our value for b, which is equal to lots of 9, 0.9999999 c. Okay, so now we've got the speed and we've got the time, and so the distance is equal to 0.999999 times 3 times 10 to the 8 times the time. Wouldn't actually matter if we just put that as 1, we'd get the same thing. Okay, so that ends up being 1,139 meters, which is equal to 10.1 kilometers. Okay, so we know that from when it hits, it travels down some distance, which is 10.1 kilometers, but the question's actually asking us for this distance here. So our answer is equal to 120 minus the 10.1, and so that is equal to 110 kilometers. So it decays 110 kilometers above sea level. Okay, so this is problem 6, and in this one we're told that quasars radiate energy at a rate, so the power is equal to 10 to the 41 watts. And we're asked at what rate is the mass of this quasar being reduced to supply this energy. So we're going to need to use our equation E equals mc squared to relate the energy to the mass. And remember that power is the rate of energy use. So power is equal to energy over time. So using this power equation, well, we've got energy is equal to power times time. So that's 10 to the 41. And we're asked to express our answer in solar masses per year. So what we'll want to know is what's the total amount of energy that's radiated in a year. So watts, that's SI units, which is equivalent to joules per second. So what we're going to need to do is multiply this by the number of seconds in a year, and then we'd end up with the number of joules in a year. And so if we multiply this by 365 by 24, so that's days in a year, hours in a day, and then we need minutes in an hour, and then seconds in a minute, that's going to give us the energy in joules per year. And so we end up with mc squared, which is E, is equal to, solving this, 3.1536 times 10 to the 48 joules per year. And what we're trying to get is m. So m will be equal to this divided by c squared. So now we're going to divide it by, remember c is equal to 3 times 10 to the 8. So we're going to divide it by this squared. And when we do that, we get m is equal to 3.504 times 10 to the 31. And that's in kilograms per year, because we're still in SI units for the mass. But what we're asked is in solar masses per year, and one solar mass is equal to 2 times 10 to the 30 kilograms. So we divide this by this to end up with solar masses per year. And so the mass is going to be equal to 17.52, which to two significant figures is 18 solar masses per year. So there you go, a really active, well, a normal quasar, which is very active, is burning around about 18 suns, and by burning we mean completely converting all the mass to energy per year. Okay, so question 7. We're told that the rest mass of the electron is equal to 0.511 mega electron volts on c squared, and that in this case the total energy of our electron is equal to 6.00 mega electron volts, and then we're asked to find its speed and its momentum. Okay, so in this case we're going to need to use our equation that the total energy is equal to mc squared over the square root of 1 minus v squared on c squared. We can rearrange this and get the square root of 1 minus v squared on c squared is equal to mc squared over E. And now what we can do is substitute in our values. We've got 0.511 mega electron volts on c squared times c squared. So this is divided by c squared, that's times c squared. Those are going to cancel out, over E, which is 6 mega electron volts. Now, if I'd wanted to, I could have converted from mega electron volts to joules. In this case, they cancel out, so there's no point doing that. I save a little bit of time doing this, and I end up with 0.085167. Okay, now what I'm trying to get is the speed. So I want v by itself. So let's square both sides. So I've got 1 minus v squared on c squared is equal to this thing squared, which is equal to 7.253 times 10 to the minus 3. Now I'm going to rearrange it. So v squared on c squared, I've moved this over to this side and this over to this side, is equal to 1 minus 7.253 times 10 to the minus 3. And so v is equal to c times the square root of 1 minus 7.253 times 10 to the minus 3. And that is equal to 0.996 c. So I've now got my speed, so that's my answer to part A. To part B, it asks us to calculate the momentum. So we'll need P is equal to mv over the square root of 1 minus v squared on c squared. Okay. M, that's 0.511 mega electron volts on c squared. V, that's 0.996 c. And this thing is unitless, it's this number up here, we calculated it here, 0.085167. Okay, so you can see one of these C's will cancel one of these. So the units is going to end up as mega electron volts on C. And putting everything into the calculator, I end up with 5.98 mega electron volts on C.